Hello everyone. I am finally ready to give you the first lecture of content here with our online instruction. And I learned a few things to try and make the experience better for you. I know it's been a while since we talked about any of these topics, but I'm going to try my best to refresh our memories and so that we can be in a position to move forward. I want to wrap up the loose ends of Module 8. So when we discussed Module 8, I got the impression that it seemed like many of you were a little bit stressed about the number of topics that we covered. But I wanted to point out that if you refer to your syllabus, what's actually expected in Module 8 does not involve a whole lot in the way of computation. There are really only two things that you're expected to be able to calculate. And due to the time that we lost in the interest of making up for some of that time, I'm going to whittle the expectations down a little bit further for you and simplify them a bit more so that these 2 bullet points that I've just crossed out are not going to be included among those expectations for Module 8, which really just leaves you with the 3 remaining bullet points, 2 of which involve actually calculating something. One is that mathematical description of the oscillating voltage as a function of time and the root mean square power that we discussed, and the other is being able to calculate the resonant frequency in an LC circuit. And then the only other thing you'll need to know for Module 8 will be that analogy that we drew between an LC circuit and a mechanical mass spring system. So getting to the first of those mathematical things, the first bullet point had to do with the oscillating voltage as a function of time. And we decided that essentially, as a function of time, the voltage is going to oscillate in a sinusoidal manner, just as you're seeing in this equation here that we discussed last time. And then also, as a result of that, the current is also going to be oscillating as a function of time from an AC power source. So that's also a sinusoidal sort of oscillation. And when you use the equation that relates power to current and potential, then you see that that turns out to be, if you just plug those 2 equations into P equals IV, you end up with a sine squared function for the power as a function of time, which means that if we think about the power as an average value, then its average value will end up being 1/2 of the I naught times the V naught, since the sine squared function on average is going to give us 1/2 for the value there. Another way to look at that is to think about the current and the potential as each contributing a 1/√2 to that prefactor there, and then we would call that together the I naught over √2, the RMS value for the current, and likewise the V naught over √2 would be the RMS value for the potential. And so that's just some jargon for you to keep in mind, that that means root mean square. So I wanted to do an example for you with these mathematical descriptions and what you might encounter for a problem of that nature. So what you're seeing here is a problem that gives you a certain frequency and a V naught and asks you what the voltage will be after a certain amount of time. And so if I can bring up my drawing tool here, I'm just going to rewrite the equation that we just saw on the previous slide. Remember that it depended upon the sine of 2 pi f times t. Okay, and for this particular frequency of 120 hertz, that's one thing, but one thing I want to point out is the time being 8.33 milliseconds. That's the same as 0.00833, which is approximately 1/120th of a second. which you can see from the frequency that if I plug in 120 hertz and then 1 over 120 for the seconds, then that's going to cancel out, and I will get a voltage that's going to be proportional to sine of 2 pi, and sine of 2 pi is just going to give me 0. So this whole thing will vanish at that particular instant in time. Okay, and then the other part of the question is asking me for this circuit what the average power will be. So using the equation from the previous page where the power was 1/2 I naught times V naught, and I've been given an additional value here, which is the I naught of 10 amps. If I plug that in, then I have one half of 10 amps times 20 volts, and so that's going to give me a power of 100 watts. Okay, so that's a kind of thing you might encounter when you're asked to calculate something related to the oscillating voltage or the power that results. Okay, so moving on to the conceptual thing that you need to know for an LC circuit. Remember that this is, when we discussed this before the break, we talked about the fact that an LC circuit is basically consisting of a capacitor and an inductor in a circuit where essentially the stored energy oscillates back and forth between the electric field and the magnetic field, because energy is stored alternately in the capacitor and then the inductor. And when it's stored in the capacitor, it's stored in the electric field, and when it's stored in the inductor, it's stored in the magnetic field. So essentially the capacitor is going to charge up, are going to be totally charged, and then release the charges through the circuits, which will then store the energy in the inductor, and then that will push the current back the other direction so that the charges on the plates of the capacitor are essentially now reversed from what they were before, and the energy is now stored in the electric field again, which it now can send through the circuit, through the inductor, and go back to the storage in the magnetic field. And so this oscillation just then repeats cyclically. Of course, in the real world, there's going to be some sort of resistance, just like there's some sort of friction in your mass spring system, so this couldn't go on necessarily indefinitely. But it's the same idea as the mass spring system, in the sense that energy is oscillating between the potential energy stored in the spring and then the kinetic energy that results from the mass that you see here moving. So it will reach a point where it has all of its energy in the potential energy when the string is fully stretched and the mass is at zero velocity, meaning that it has no kinetic energy. And then it will reach a point where all of the energy is being stored or being manifested as kinetic energy when the spring reaches its equilibrium position. And then the spring will keep going on and compress, and then reach a point where the mass reaches an instantaneous rest and all of the energy is stored in the spring potential energy again due to the compression, and then it will go back the other direction again and continue on. So that's the idea and the analogy that you want to draw between an LC circuit and a mass spring system. And then the final bullet point that we needed to know for Module 8 is how to calculate resonant frequency for an LC circuit, and that's given by this formula that you see here. Now, you may not necessarily be calculating the frequency per se, but you may need to just otherwise work with this particular equation. So I wanted to give you an example in which you would have to use this kind of equation. In this example, you've created an LC circuit and you know what the inductance of your inductor is, but you do not know what the capacitance of your capacitor is. So you could tune the frequency to find out where the resonant frequency occurs. And in this example, it occurs at 100 hertz. And so you can use that information to then deduce what the capacitor's capacitance must be. So, whoops, let me go back to that for a second. I meant to bring up my pen again, if it will let me. There we go. And so if, let's go back. Okay, if you take the equation that we just discussed, where the resonant frequency is going to be 1 over 2 pi times the root of L times C, and we rearrange this in order to solve for C, then that's going to tell me that C is going to be 1 over 4 pi squared times the inductance, all in the denominator, times the resonant frequency. So if I plug in what the inductance is here, 40 henries, and the frequency of 100 hertz, what I should find is a capacitance in this example of about 79.6 microfarads. So you can work that out on your own on your calculator and verify that that's the number that you get. But again, that's the only other calculation that you would need to do for this particular module. Okay, I appreciate your listening. Again, as I had said before, these lectures will be shorter than usual. Hopefully the next one will be a little bit longer than this one, but I wanted to just basically recap what we discussed last time, so that's why this one's in particular short. So I will talk to you again in a future lecture. Thanks.